Hello viewers, welcome to the Pragati Engineering College e-learning system. In this video lecture, I will explain the Wiener filter. So, next. So, at the onset, I will explain the classical digital filter characteristics. In this, I will tell why the classical digital filter cannot estimate the signal. Then next, we will go to optimum filter, of which the Wiener filter belongs to. Then we will go with adaptive linear combiner. It is the basic block of Wiener filter. Then we will go to the details of Wiener filter, how it works. Then some applications. Then shortcomings. Next. So here we will explain the classical digital filter characteristics. So this is a ideal low pass filter where the frequency response is 1 when the angular frequency is less than or equal to omega c, that is cutoff frequency, and 0 when it is more than omega c and less than pi. The impulse response of the ideal low pass filter Hn is equal to omega c by pi for n is equal to 0 and omega c by pi into sin omega cn by omega cn when n is not equal to 0. So this is the plot of the impulse response of the ideal filter. So here we see that impulse response exists for n is positive and n is negative. But we know that so in LK system, if causal, then Hn is equal to 0 for n is negative. But here we are getting non-zero values for n is negative. Hence, this cannot be realizable. This is a non-causal system, and this cannot be realizable practically. Next. So this is the magnitude response of a ideal low pass filter and a physically realizable low pass filter. So this is the magnitude response of the ideal low pass filter, and here we see that from within this is the pass band, this is the stop band, and within the pass band, so it is constant, gain is constant, and within the stop band, so for ideal filter the gain is 0. But in the physically realizable low pass filter, so we see that in the pass band there are ripples, in the stop band also there are some ripples, and there is a transition band. So we can optimize the low pass filter by reducing the ripples and reducing the ripples in the stop band as well as in the pass band, and reduce the transition bandwidth. So next. So here we see that the classical filter depends on the frequency specification, because the classical filter, whether it is low pass, high pass, band pass or band stop, etc. So it depends on the frequency. We have to specify the frequency range to extract information from a signal in an idealized environment. So what is idealized environment? So idealized environment is here when the noise is 0. So when noise is 0, we can estimate perfectly the signal, the desired signal. If there is noise, so it is difficult, and if the SNR is very low, then it is impossible to estimate the desired signal. So estimation of signal in noisy environment is not possible by a classical filter. So we take a different view of filtering, that is optimal filter. So because the classical filters cannot estimate the desired signal in the noisy environment, so we are taking a different filtering techniques, that is optimal filter. And the Wiener filter belongs to optimal filter class. So now comes to the optimal filter. The optimal filter filters the observed signal Xn. So it is observed signal because it is received signal, it contains noise also, signal and noise. So Xn desired signal Dn plus noise, to modify it such that it approximates the desired signal Dn in some statistical sense. So we'll see what is the statistical sense. So we will come to the Wiener filter. The output of the filter Yn is a good estimate of the desired signal Dn. The output error, so when we are estimating, so estimated signal is not the exact signal, so we say it is d to the Dn cap. So this is the estimated signal of the desired signal. So the output of the Wiener filter is d cap n, so which is not exactly same as the desired signal. So we get some error which is denoted as En, and it is nothing but the difference of Dn and d cap n. So most important thing is this is a time domain specification filter, where the classical digital filters are frequency domain, it is the time domain specified filter. Next. So now we come to the adaptive linear combiner. The adaptive linear combiner are two types. One is multi-input adaptive linear combiner. Second is the single input adaptive linear combiner. Previous. So here this is a multi-input adaptive linear combiner, and here we see that there are L plus 1 number of inputs, x0n, x1n, xln. So n denotes the time, and this is the 0th input, first input, and lth input. And here we find that some weights W0, W1, Wl. This can be either real or complex. And this arrow marks is that so we can vary the output. So that means as we can vary depending upon the some statistical sense, so it is known adaptive. So and why it is linear? So here we will get x0n into w0. Here we get x1n into w1. Here we get xln into wl. So it is a adder, and yn is nothing but x0n into w0 plus x1n into w1 plus xln into wl. So that means the output of the adaptive linear combiner is nothing but it is linearly related with the set of inputs. So that's why it is linear, and combiner because it combines the input. So adaptive because we can vary as according to our requirement, and it's linear because the output is linearly related with the input, and it's a combiner because of this. So it is known as adaptive linear combiner, and it's multi-input. Next. So this is the second type of adaptive linear combiner, where the single input, and we find here there are some delay units. So this is the first delay unit, and the output of the first input of the first delay unit is xn. The output is xn minus 1 unit delay. Then in second delay unit, so here you get xn minus 2. Okay, here is the bracket. So it is the last delay unit, and we get here the output as xn minus n. So all these are the input signals, and here this input signal is multiplied by the weight w0, which also can vary as in the previous case. So here this input xn minus 1 also multiplied by w1, which also varies. So here we get xn minus 1 w1, here we get w0 into xn, here we get xn minus 1 into w2, here we get wl into xn minus l, and here all are added, and you will get yn output. Again here also the output is linearly related with the input, so it is known as the linear combiner, and as the weights can be varied, so it is adaptive. Weights can be adapted, so it is adaptive linear combiner. But so if you take different sets of input, the adaptive linear combiner is not linear, it is non-linear, but we say it is linear combiner because for a fixed set of input, so it behaves linearly, that's why it is known as adaptive linear combiner. Next. So here what I told that yn is expressed in terms of the input and weights. So this is the compact expression, and this is the expression in terms of matrix, where xt means x transpose, where x is the L plus 1 by 1 matrix, which is nothing. This is xn minus 1, xn minus 2, up to xn minus n. And w similarly, w0n, w1n, wln transpose. So interchangeably, so either we can yn can be this one or this one. So anyone we can use, we can interchange this, there is no problem. But both are they give the same result, that is yn. Next. Okay, so now we come to the Wiener filter. As I told you, the Wiener filter, the basic block is transversal filter, so which is a single input adaptive linear combiner. This is a linear type invariant circuit. Okay, so here is xn, and you can say that xn contains both the desired signal and the noise. So here is the d cap length. So cap indicates that is the estimated value of dn, and dn is nothing but the desired signal. and this is a order circuit. So here the output gives the difference between Dn and d cap n, which is known as the error. So error En is nothing but Dn minus d cap n. The weights of the transformer filter is adjusted using the minimum mean square estimates. So, so here the transformer filter is nothing but that what we see in the before the figure, that is a single input adaptive linear combiner, and the weights can be varied taking this En value. Next. So here error function En is nothing but Dn minus d cap n. So and d cap n, you know that it is nothing but the E, that is Yn, and I have taken here W transpose into X. I can also take X transpose W, but here it is more suitable to take W transpose into X. So now mean square error. So what we do? So taking the error function, we will square it, we will find out the mean. So we have taken En, we square it, then we have taken the expectation, that is mean. So this is nothing but, if you put the value of En, then it is Dn minus W to X, square, and then expectation. And we expanded it, so it is like this: E of d square n plus Wt E of X into X Hermitian transpose. So why it is Hermitian transpose? Because when we take the expectation, it is nothing but X. So the vector and the complex conjugate. So the that XH is nothing but X complex conjugate and then transpose. So I have taken XS is W minus 2E into Dn XH W, and here it is E of d square n plus Wt Rx. So Rx is nothing but E of X into X Hermitian, and Wrx is known as input correlation matrix. So here if you see that the mean square error at a particular point is a single value, and this also gives single value. Here it is a 1 by L plus 1 matrix, that is Ra. So here this one is a L plus 1 by L plus 1 matrix. This one is a L plus 1 by L 1 matrix. So if you multiply, so it will be a single element. So similarly, here also this one is a L plus 1 by 1 matrix, and this is one is a 1 by L plus 1 matrix. So when you multiply, it also gives single element. So this is a single element, this is a single element, this is a single element. So this one is also a single element. Next. So here we see that same thing. So what I explained just now. So Rx is nothing but E of X, X complex conjugate transpose. That is nothing Hermitian transpose equal to H. So here E is equal to Xn, Xn minus 1, Xn minus 2 up to Xn minus L. So it is a complex conjugate Xn complex conjugate by Xn minus 1 up to X complex conjugate X n minus L. So when we multiply, we see that here we get this one is multiplied by this one, Xn into X complex conjugate n, then expectation, so it gives the correlation at point 0. And when we multiply Xn with X complex conjugate n minus 1, it gives R1. So similarly, we have formed the matrix, the correlation input correlation matrix. So here we get R complex conjugate of 1. So because here X n minus 1, when we multiply with the X complex conjugate n, so we get R of minus 1. R of minus 1 is nothing but R complex conjugate 1. So now you see, so this input autocorrelation matrix, so this is the principal diagonal, and all the elements of the principal diagonals are same. So you take also any other diagonals, so all the elements of each and every diagonals are same. And here, due to it is Hermitian, so it is this is the value, any element, ij element is same as complex conjugate of ji element. So it is the first row and second column, this is the second row and first column, both are complex conjugate. Similarly, this one is the first row and L plus 1 element column, and here it is L plus 1 row and first column. So both are complex conjugate. So Rx is a L plus 1 by L plus 1 Hermitian Toeplitz matrix known as input correlation matrix. So, and here if you take the Rx transpose, it is nothing but it is same, Rx transpose is same Rx. So it is twice because the diagonal, all the elements of each diagonal are same. That's why it is twice. It is Hermitian because of this ij element is a complex conjugate of ji element. Next. So it is the cross correlation matrix Rdx is called cross correlation matrix of the desired signal with the input. So this is the desired signal. We have taken the complex conjugate and transpose. So this is a 1 by n plus 1 cross correlation matrix of desired response dn and the input. So now, we see that this chi, which is the mean square error, is nothing but expectation of d square n plus wt rx w minus 2r dx transpose w. So it is a quadratic equation. How it is a quadratic equation? Or what is quadratic equation? It is nothing but x square plus bx plus c. So x is the variable and a is a constant. So here you see the weights are variable. So we say here in electrical engineering we say weights, in mathematics they say coefficients. So here the weights are variable. So this is your x, this is your x. So we are getting x square and this is a constant. So a, and here it is x. So minus 2r dx now it is nothing but b, and here it is c. So ax square plus bx plus c. So it is a quadratic equation. So a two-dimensional error function chi is of a bowl shape as shown in the figure. You see the figure in the next slide, right? And it is concave upwards and contours of the constant mean square error. So here these weights are L plus 1 number of weights. L plus 1 number of weights. So all are in matrix form. These are in matrix form. This is not a single element. So here there are a set of weights. So we can vary the weights. We can vary the weights to get a particular error. For different set of weights, the error is different. So taking different set of weights, so if we want to draw the error function, so this is known as the performance function or the mean square error function, and it is a L plus 2-dimensional case. So if L is very large, that means it is more than 3, then it is impossible to draw the error performance function. So what we will do to see how the error performance function looks like. So we will take only two weights, that is W1, W2, instead of taking W0, W1, W2 up to WL. So we will take only two weights and see how the error performance surface looks like. Next. So we have taken here W1, we have taken here W2, and this is the error surface, mean square error surface. So we see that it is a bowl shape, just like a bowl, and the bottom of the bowl is the lowest point, and here the upper side of the bowl is towards here, it is concave in upwards, it is concave in upwards, and this is the bottom point. And so there are so many points on the error surface. So you take any point. So here I have taken one point. So for this point, the set of, that means here the set of weights are only two, that is W1 and W2. So similarly, set of weights can be any number. So here, this is, or this at this point, so there is a particular set of weights, that is W1 and W2. Similarly, for this point also, it's particular set W1 and W2. So now the question is, so how to get the minimum point? The minimum point, how to move to the minimum point? So we'll see. And one more thing is, so if you take a slice which is parallel to this plane, W1 and W2 plane, then we'll find some contours, and all the points of the contour have the same value. That is a particular value of the error function chi. So, and how to move this one? Because at this point, only error is the least, and we want that when the error is minimum, then we will say that the estimated value d cap n is very close to dn, and we say that the weights at that point is optimum value. That's why it is known as optimum filter, because we have to optimize the weights to minimize the error function. So, and how we'll do it? So we'll choose any point here and find out the gradient here, and gradually we'll move downward, 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 and here we'll come to this point. Next. So here gradient at minimum mean square error. So this is a gradient. That means we have to take the partial differentiation of the mean square error with respect to the weights. So weights, because it is a vector, so that it is nothing but delta chi by delta omega w0, delta chi by delta w1 up to delta chi by delta wl transpose, because it is a column matrix. It is a column matrix. So now, so if you see, so what is chi? Previous, then okay. So this is chi. So now, if I partially differentiate this equation with respect to w, then this is a constant, so it will be 0, and here it is 2x, so that we will get here 2 rxw, and here we will get 2 r dx transpose. Next, previous. Okay, so that means this is nothing but 2 rxw minus 2 rdx. So to obtain, that means this is the after the partial difference. That means when find out the gradient, and gradient will be 0 when this gradient will be 0. So that means, so this is equal to 0. So this is equal to 0 means, and the weights of the vector w becomes the optimal and denoted by w0. So w0 means is optimal weights. So that means when the gradient is 0, so only at that point we get the optimal weights. Next. So here 2 rx w0 wo is equal minus 2 r dx is equal to 0. So that is rx w o is equal to r dx, that is Wiener equation we say, and w0 is nothing but rx inverse into r dx. That means, so this is your optimal weights. So that means optimal weights, we can say that it is w0 o, w1 o up to wl o. So this is the vector, and we say that this is equal to w1. So optimal weights. So it is nothing but, so we will first we have to find out, so what is the measured signal? We are measuring the signal xn. So we find out the correlation function Rx, then take the inverse and find out the cross correlation matrix, that is Rdx, then multiply this will give you the optimal weights. So at the optimal weight, so what is the error? Error actually cannot be 0. So what is the error we are getting? So E chi mean is equal to E d square n plus w0 transpose Rx w0 wo minus 2 r dx transpose wo. So that is equal to, what is w? W is nothing but Rx inverse into r dx. So if you put, so this one into this one is the identity matrix. So that what we are getting, that is r dx w0, and here also r dx transpose w0. So this one cancels, so it is nothing but. So this is the minimum value of the mean square error. So when w is equal to w at the optimal points. Next. So principal orthogonality. So what is principal orthogonality? So principal orthogonality we defined. So when at the optimum point, that means when w is equal to wo. So en is equal to dn minus d cap n is equal to dn minus x transpose wo. So and now we find out the expectation of en with the input at the point of the optimal point. That means, so here E into dn into x complex conjugate minus E into expectation into x minus xs into wo. So that is equal to, so r minus this one is 0. So that means this shows that, so the above derivation shows that at the optimum weights, that means when w is equal to wo, the expectation of error and inputs, this is the expectation of error and inputs is 0. That is, the error and outputs are orthogonal to each other. So that means wo and the input x are orthogonal to each other only at one point, that is minimum mean square error. Next. So now we see some applications. So we'll consider three applications: one is filtering, one is prediction, and another is noise cancellation. So in filtering is nothing but what we have explained previously. It's the same. So input xn is nothing but a dn plus dn, where dn is the noise, and we assume that the noise dn has zero mean and is uncorrelated to signal dn. So this is one of the shortcomings of the Wiener filter. Okay. So as Vn is uncorrelated to the signal Dn, so expectation of Dn into E star n minus k is equal to 0. So therefore Rdx k is nothing but this one is Rd. Okay, because if we put here, this is x d n minus d complex conjugate n minus k plus d complex conjugate n minus k. So then again we will get two factors, taking dn and vn, and then dn plus dn. So dn plus expectation of dn with dn is 0, and we will get only expectation of dn with dn. So that is known as the rdk. So similarly, rxk is nothing but this one, and it is nothing but rdk and rgk. So, and the Wiener off equation in case of filtering is nothing but this is Rd minus Wo into Rd plus Rv is equal to 0, because we have taken Xn is equal to Dn plus Dn. Next. So now come to the linear prediction. So in linear prediction, what is the desired signal? Because in prediction means we will predict the future value. So if some inputs are known to us, then taking these inputs, so we will predict the next input. So xn is known to us, xn is known to us, xn minus 1 is known to us, xn minus 2 is known to us. Similarly, some of the past inputs are known to us. So taking the past input and present input, so we will predict the future input, that is xn plus 1. So xn plus 1 is here the desired signal which we have to predict. So this is the block diagram, and this is the Wiener filter. So whatever the block diagram in the Wiener filter, it is included here only. So now it is xn, and here is vn, that is noise. So here we are getting yn is nothing but xn plus vn, and that is the input to the Wiener filter, and the weights are adjusted in such a manner that it estimated, this output is nothing but the estimated value of the input signal xn plus 1, and this is nothing but your desired signal estimated value. So here, in the absence of noise, yn is equal to xn, okay, fine. So the output of the FI filter is xn plus 1 cap, that is the desired signal. This is nothing but, as you have seen, that it is wk yn minus k, because it is basically a transversal filter, and here ry, that is because here Wiener filter input is yn, so we find that the ry, that is input correlation matrix or correlation matrix of signal y, and this is nothing but rx plus rv, because yn is equal to xn plus dn. And Wiener equation is rywo minus rdy. So wo is nothing but ry inverse rdy. So it is nothing but the cross correlation between the desired signal, which desired signal is nothing but x cap n plus 1, and yn is nothing but xn plus dn. Next. So this is noise cancellation, the third application. So where we need to this noise cancellation, where we will use. Suppose a pilot in the aeroplane is communicating with the base station. So when the signal is coming, so his noise generated by the engine itself. So now he is not able to, due to noise generated by the engine, he is not able to listen clearly the voice of the person in the ground station. So then how to eliminate that noise? So put that noise, suppose I am the pilot, I have a microphone and I have an earphone, so it is being disturbed because of the noise engine. So what I will do, I will keep another microphone in the distance. So noise is here, another second microphone is here, and fast microphone here. So it is the signal source. That means this is the signal source. This is DN. This is noise source. Noise generated by the engine. So this is the primary sensor. So we can say that it is the microphone 1, and here is the secondary sensor, that is microphone 2. So though the Vn is the input both the primary sensor and secondary sensor, the output due to Vn here is V1n, and the output due to this secondary is V2n, because the distance. So distance is different. So, and this V2n, the second noise, so it is the input to the Wiener filter. So, and we have to adjust the weights in such a manner that the output is an estimated value of V1n. Okay. So that if we can adjust perfectly and at optimum point, so the difference between V1 cap n and V1n is very small. So now we just add it. So En is nothing but xn minus V1n. So it is nothing but D cap n. So that is the desired signal. So this is how the noise cancellations perform. Next slide. So the Wiener equation in this because this is the V2 is the input to the Wiener filter. So we have to take the autocorrelation matrix of V2. This is RV2. This is W0, optimum value of the weights, and this is the V1 and that is cross correlation matrix of V1 and V2, because V1 is the desired signal here and V2 is the input signal. So the cross correlation matrix we have to take from the desired signal and the input signal. So it is RV1 into V2. So here, so this is RV1, where RV1 V2K is nothing but this one. So we know it because in matrix from before. So it is E of what is V1 xn minus Dn into V2 complex conjugate n minus k. So now if you multiply, so we are getting these two factors, and so if these two are uncorrelated, that is V2 and D are uncorrelated, so this factor will be 0 and we will get this one. This is nothing but Rx D2K. So if V2 and V2n and D8 are uncorrelated, so this factor is 0, and the Wiener equation is RV2WO is equal to RxV2. Next. So here what I have to explain is the same thing. Next. So now the shortcomings, the few shortcomings I have written. So it is a linear shift time invariant filter. It is not an nonlinear filter. So, and we know that all the systems are nonlinear in nature. So here is a linear shift time invariant filter, and the desired signal and the noise are assumed to be wide sense stationary process. So this is the main shortcomings of the Wiener filter. And the second one is noise is assumed to be zero mean and uncorrelated to the desired signal. So we cannot say whether noise is zero mean or not. And does not estimate the non-stationary signal. So this is another very important one, because practically we cannot use in nonlinear filter because almost all the signals are non-stationary in nature. So for non-stationary case, the Wiener filter cannot work. So we'll go for a different type of filter, that is Kalman filter. So we'll discuss in some other video lecture about Kalman filter. So for today, it is. Thank you.